We thought we understood the universe. We thought it was expanding, smoothly, steadily, predictably, from a single, violent beginning 13.8 billion years ago. We thought galaxies formed in a slow architectural sequence, dark matter scaffolding first, stars igniting later, structure rising like cities from cosmic dust. We thought the early universe was dim, chaotic, embryonic. And then the James Webb Space Telescope opened its golden eye. What it saw was not a younger version of our universe. What it saw looked mature, massive, structured, almost impossibly evolved. Galaxies too big, too bright, too organized, appearing far too early. If the light is telling the truth, and light has no reason to lie, then something fundamental is wrong. Not a number. Not a parameter. The story. And if the story is wrong, then we may not be living in the universe we thought we were. We begin somewhere safe. Picture the night sky as we once knew it. Distant stars, faint smears of galaxies, points of light that took millions or billions of years to reach us. Every photon a time capsule. When we look far away, we look backward in time. That is the quiet miracle of astronomy. Distance equals history. The farther we look, the younger the universe appears. For decades, our telescopes confirmed a simple narrative. The early universe, within the first few 100 million years, was small scale. Proto-galaxies, irregular shapes, stars just beginning to form from cooling hydrogen and helium, the first light breaking through cosmic fog in an era called reionization. Small things first, big things later. That was the rule. Then Webb looked deeper than any telescope before it. Infrared vision, tuned to catch the faintest stretched light from galaxies formed just 300 to 400 million years after the Big Bang. We expected cosmic toddlers. We found skyscrapers, galaxies with masses comparable to the Milky Way, galaxies with structured disks, galaxies rich in heavy elements, carbon, oxygen, nitrogen, elements forged inside generations of stars that should not have had time to live and die yet. The timeline cracked. Imagine discovering fully grown oak trees in a world that, by every clock, should still be covered in seeds. That is what Webb saw. And the numbers are not subtle. Some of these early galaxies appear 10 times more massive than models predicted possible at that epoch. Their stars are forming at furious rates, hundreds of solar masses per year, when the universe itself was barely out of infancy. We can try to stretch the models. We can increase star formation efficiency. We can tweak the distribution of dark matter halos. We can imagine gas cooling faster. But each fix strains something else. Because cosmology is not a loose web of guesses. It is a tight lattice built from the cosmic microwave background, the afterglow of the Big Bang, measured with exquisite precision by missions like Planck. That background radiation locks in the amount of matter, and dark energy in the universe. It constrains how fast structure can grow. There are limits, and Webb is pressing against them. So what are we seeing? Possibility 1. The galaxies are not as massive as they look. Early estimates rely on interpreting infrared light shifted by expansion across more than 13 billion years. Stellar populations at those redshifts are complex. Dust can masquerade as mass. Young stars can outshine their weight. We could be overestimating, but follow-up spectroscopy, detailed measurements of chemical fingerprints, has confirmed some of these objects are indeed extremely distant. Some are indeed surprisingly massive. Possibility 2. Galaxies form faster than we thought. Perhaps gas collapsed more efficiently in the early universe. Perhaps feedback from supernovae, normally thought to blow gas outward and regulate growth, was less disruptive in those first few 100 million years. Perhaps the first stars were far more massive, burning bright and dying fast, seeding heavy elements quickly. But to reconcile the observations, the efficiency would have to be extreme, uncomfortably extreme. And then there is the deeper possibility, the one that whispers at the edge of the data. What if the underlying cosmology is incomplete? Our standard model, lambda cold dark matter, assumes dark matter is slow-moving, cold, clumping early and forming gravitational wells. It assumes dark energy, represented by the cosmological constant lambda, accelerates expansion uniformly. It assumes initial fluctuations seeded by inflation grew at predictable rates. But what if dark matter behaves differently at early times? What if the expansion rate was not exactly what we inferred? What if the early universe contained exotic physics, additional energy components, interactions, or fields that accelerated structure formation? These are not wild fantasies. They are adjustments to equations. But even small changes ripple across billions of years. Change the expansion rate slightly, and galaxies can assemble earlier. Modify dark matter interactions, and collapse times shift. Allow early black holes to form rapidly, primordial seeds growing to millions of solar masses within hundreds of millions of years, and they can anchor massive galaxies faster than expected. Webb has also seen surprisingly large black hole candidates at extreme distances. Quasars blazing when the universe was less than 1 billion years old. Engines too powerful, too early. Black holes that should not have had enough time to grow from stellar remnants. Unless the seeds were bigger, unless accretion was more efficient, unless something about gravity itself behaved differently in those dense early epochs. And this is where the emotional ground tilts. Because if the early universe formed structure faster, heavier, brighter than predicted, then the entire arc of cosmic history shifts. The universe becomes less gradual, less patient, more explosive, more capable. We are used to imagining a slow unfolding. Webb suggests a universe that leapt, and that leap has consequences. If galaxies matured earlier, then stars ignited earlier. If heavy elements formed earlier, then planets, rocky, metal-rich worlds, could have emerged sooner than we ever believed. The timeline for habitability stretches backward. The stage for life may have opened earlier, and suddenly, this is not just about galaxies. It is about us, because every carbon atom in your body was forged inside a star. If stars were thriving sooner, then the ingredients for biology were circulating earlier across the cosmos. The universe may have been chemically ready for complexity long before Earth existed. We stand under a night sky that now feels less like a beginning, and more like a continuation of something already ancient when it was young. We have to feel what that means. 400 million years after the Big Bang sounds vast, until we compress it. Imagine the entire 13.8 billion year history of the universe as a single calendar year. January 1st, the Big Bang. December 31st, 11:59 p.m, us. In that calendar, 400 million years lands in mid-January. Mid-January. We expected cosmic darkness, a few sparks, hydrogen clouds hesitating before gravity. Webb is showing us cities already lit. That compression matters because cosmology is a race between gravity and expansion. Gravity pulls matter inward, building structure. Expansion stretches space outward, thinning everything apart. In the early universe, expansion was faster. Space itself was swelling more rapidly than it is today. Galaxies had to fight harder to assemble. Picture trying to build a sandcastle while the beach itself is stretching beneath your feet. And yet, there they are, massive systems emerging in a universe barely past its first breaths. To understand how destabilizing this is, we have to step inside the old expectation. After the Big Bang, the universe was hot plasma, protons, electrons, photons tangled together. About 380,000 years later, it cooled enough for atoms to form. Light decoupled and streamed freely. That ancient light is still with us as the cosmic microwave background, a nearly uniform glow with tiny fluctuations, temperature differences of 1 part in 100,000. Those tiny ripples are everything. They are the seeds of all structure. Regions slightly denser than average pulled in more matter over time. Dark matter, silent, invisible, collapsed first. Ordinary gas followed, falling into those gravitational wells. Stars ignited. Galaxies formed hierarchically, small halos merging into larger ones. Bottom up. Slow accumulation. That framework worked astonishingly well. Simulations run on supercomputers, fed the exact fluctuations measured in the microwave background, produced a universe that looked statistically like ours. Galaxy clusters, filaments, voids, the cosmic web. The model became confidence. But Webb is peering into the era where those first halos should still be modest. And instead of modest, we see luminous giants. Some early galaxies appear to contain tens of billions of solar masses in stars. To build that much stellar mass so quickly, enormous amounts of gas must have collapsed and converted into stars with extreme efficiency. Nearly every available baryon, normal matter, would need to participate. It is like expecting a village and finding Manhattan. And then there is brightness. These galaxies are not only massive, they are intensely luminous in ultraviolet light, which means active star formation. Hot, young, massive stars pouring out radiation. The rate at which some of these galaxies form stars rivals or exceeds that of starburst galaxies billions of years later. This suggests something else. The early universe may have been less dusty than we thought. Dust absorbs ultraviolet light and re-emits it in infrared. If there was less dust, light escapes more freely, making galaxies appear brighter. But dust is created by stars, which means stars must have already lived and died to create it. And we circle back to the same tension. Time. There may not have been enough. Unless the first stars, the so-called population 3 stars, were enormous, hundreds of times the mass of our Sun, burning fast, exploding as supernovae within a few million years, seeding space with heavy elements at a breakneck pace. If that is true, then the early universe was not gentle. It was violent, efficient, incandescent. We imagine the cosmic dawn as faint. Webb hints it may have been blinding. And then the black holes. Some early galaxies show signs of active galactic nuclei, supermassive black holes feeding and shining as quasars. To reach millions or billions of solar masses so quickly, these black holes would have to grow near the theoretical maximum rate, Eddington limited accretion, for extended periods. Even that might not be enough. Unless the seeds were not ordinary stellar remnants of maybe 10 or 100 solar masses, but massive, direct collapse black holes, born from pristine gas clouds collapsing without fragmenting into stars. Or something even more exotic. Primordial black holes, perhaps, formed from density fluctuations in the earliest moments of the universe. A speculative idea, but one that gains emotional weight when observations press against standard growth timelines. If such objects existed, they could accelerate galaxy formation dramatically. The implications ripple. Because cosmology is constrained from multiple directions, the microwave background gives us the early conditions. Large-scale galaxy surveys map the current structure. Supernova observations reveal the accelerating expansion driven by dark energy. All these datasets interlock. If Webb is revealing a universe that assembled faster, then either our interpretation of these early galaxies is incomplete, or some piece of that interlocking framework needs adjustment. And adjustments at cosmological scales are not minor renovations. They are architectural. Imagine discovering that the blueprint used to build a city was slightly wrong, not in a window measurement, but in the foundation's curvature. You would have to re-examine every building. There is another layer, more subtle, but just as destabilizing. The expansion rate of the universe today, measured locally using supernovae and Cepheid variables, does not perfectly match the rate inferred from the early universe via the microwave background. This discrepancy is called the Hubble tension. It is small in percentage terms, but enormous in implication. If Webb's early galaxies are genuinely more mature than expected, they may be connected to that tension. Perhaps the expansion history between the early and late universe is not as smooth as assumed. Perhaps dark energy evolved slightly over time. Perhaps an additional early energy component, sometimes called early dark energy, altered growth rates. These are careful ideas, mathematical, testable, but emotionally they hint at something dramatic. The universe may have changed character as it aged. Not wildly, but meaningfully. And we are only now seeing the evidence. Step outside for a moment. Look at your hands. The atoms inside them formed inside stars that died billions of years before Earth coalesced. You are already a product of deep time. Now imagine that the cosmic assembly line that produced those atoms began operating at full intensity earlier than we thought. Imagine that somewhere 13.4 billion years ago, a galaxy was already churning out heavy elements, already forming planetary systems, already hosting environments we have barely imagined. We used to think complexity required patience. Webb suggests the universe may be inherently efficient at building it. This does not shatter cosmology into chaos, but it does crack open its confidence. The difference matters. Because when a model strains under observation, science does not collapse. It sharpens. The data are still coming. More spectroscopy, deeper fields, gravitational lensing measurements refining masses, simulations adjusting parameters, testing whether the standard model can stretch far enough. It may survive. It may bend. Or it may evolve into something slightly different, subtly revised, more nuanced, incorporating physics we have yet to fully understand. But regardless of the final equations, one thing has already shifted. Our intuition about the early universe. We no longer see it as a quiet nursery. A place where gravity moved fast, where light ignited quickly, where structure emerged with startling ambition. And that reframes our own existence. Because if the universe builds rapidly, then complexity is not a rare, reluctant accident. It may be a natural consequence of cosmic law. And if that is true, then the story of the universe is not one of slow awakening. It is one of early brilliance. And we are standing billions of years downstream from a beginning that was far more alive than we ever imagined. But the deeper shock is not just that the early universe was brighter, it's that it may have been organised. When Webb resolved some of these distant galaxies, astronomers expected irregular blobs, chaotic clumps still assembling. Instead, in several cases, they found disks, flattened structures, rotational signatures, systems that appear dynamically settled. Disks require time. To become a stable rotating disk, gas must collapse, conserve angular momentum, cool, and arrange itself into something coherent. That coherence is fragile. Mergers disrupt it. Supernova explosions stir it. Black hole feedback can blow it apart. And yet we are seeing hints of order at epochs where turbulence should dominate. This is like opening a history book to the chapter on ancient tribes and finding photographs of modern skylines. Something about early structure formation may be more efficient, more decisive than we allowed. Let's step into that early era. The universe at 300 million years old was smaller by a factor of about 10 in scale compared to today. Galaxies were closer together. The cosmic microwave background temperature was higher, around 30 Kelvin instead of today's 2.7. Radiation fields were more intense. Gas densities were higher. Gravity had more material packed into tighter volume. That could accelerate collapse. If dark matter halos formed earlier or were denser than expected, baryonic gas would fall in rapidly. Cooling mechanisms, via molecular hydrogen, then atomic transitions, could ignite star formation quickly. In that, they erupt. And if they erupt, they enrich themselves quickly with heavy elements, allowing subsequent generations of stars to form even more efficiently. A feedback loop of acceleration. But here's the tension. The cosmic microwave background is exquisitely sensitive to the amount of matter and radiation in the early universe. If structure formed too quickly on large scales, it would leave imprints, secondary anisotropies, distortions, in that ancient light. So far, those imprints are subtle, which suggests that whatever is happening must operate within narrow constraints. That is what makes this moment so electric. We are not watching cosmology explode into nonsense. We are watching it be forced into precision. Each new Webb observation acts like a stress test. Some early galaxy candidates initially thought to be impossibly massive were later revised downward after better data. Photometric redshifts, estimated from colour, sometimes overestimated distances. Spectroscopy corrected them. The universe defended itself. but not entirely. Several objects remain stubbornly distant, confirmed redshifts beyond 10, some approaching 13. That means we are seeing them when the universe was less than 350 million years old. And they are not faint whispers. They are luminous presences. This forces a recalibration of our mental map. We once imagined a long, dark, cosmic dark age, lasting hundreds of millions of years before reionization lit up the intergalactic medium. Webb's findings suggest reionization may have been driven by a surprisingly abundant population of bright galaxies. The fog may have lifted faster than expected. The first billion years may have been crowded, and if crowded, then interactive. Galaxies merging, black holes feeding, radiation carving bubbles in neutral hydrogen across cosmic volumes. This was not a quiet dawn. It was a cosmic rush hour. Now widen the lens. If the early universe assembled structure rapidly, what does that imply about dark matter itself? Cold dark matter, slow-moving particles that clump efficiently, has been the default assumption. But there are alternatives. Warm dark matter, self-interacting dark matter, fuzzy dark matter composed of ultralight scalar fields. Each changes small-scale structure formation in measurable ways. If dark matter was slightly warmer, small halos would be suppressed, delaying structure formation. That would worsen the tension with Webb's early giants. If dark matter were self-interacting, halo density profiles could shift, potentially affecting collapse rates. If it were ultralight and wave-like, interference patterns could alter early clustering. These are not speculative fantasies thrown at a wall. They are active research programs, and Webb's data feed directly into them. Because cosmology is a web of inference, we cannot see dark matter, we infer it from gravitational effects. We cannot see inflation, we infer it from statistical patterns in the microwave background. Now we are inferring early physics from the brightness of galaxies at the edge of visibility. It is an extraordinary chain of reasoning. And at its centre is light, photons that left their galaxies more than 13 billion years ago, stretched by cosmic expansion into infrared wavelengths, captured by a segmented mirror floating 1 million miles from Earth. We built an eye to look back to the beginning, and it is telling us the beginning may not have behaved the way we rehearsed. There is something profoundly human about this. We crave origins that are simple, clean arcs, gradual build-ups, clear progressions from chaos to order. But the universe may not respect narrative simplicity. It may generate complexity early, explosively, then spend billions of years refining it. If so, then our cosmic story shifts from slow emergence to rapid ignition followed by evolution. That changes how we imagine rarity. If galaxies like the Milky Way, or at least their structural ancestors, were already substantial within a few 100 million years, then the window for planet formation expands. Rocky planets require heavy elements, silicon, iron, oxygen. These elements come from supernovae and neutron star mergers. If those events occurred earlier and more frequently than expected, planetary systems may have begun forming astonishingly early. Not necessarily life, but potential. The universe may have been capable of building Earth-like chemistry far sooner than we allowed ourselves to imagine. Stand with that for a moment. Our Sun formed 4.6 billion years ago. Earth cooled, life emerged within a few 100 million years. Complex multicellular life took billions more. Intelligence, tool-making, radio signals, very recent. If other regions of the universe had a head start of billions of years, the implications are staggering. Not guaranteed, but staggering. Webb's early galaxies don't prove ancient civilizations. They do something subtler. They lengthen the runway of possibility. And that is why this discovery feels existential, not merely technical. Because when we adjust the early timeline, we adjust the depth of cosmic history in which complexity could unfold. We are no longer perched near the beginning of structure. We are living in a universe that may have been structurally ambitious almost from the start. But let's not lose discipline. Extraordinary claims require extraordinary verification. Astronomers are already conducting deeper surveys, targeting these early galaxies with spectroscopy to measure stellar populations, metallicity, and dynamics more precisely. They are refining mass estimates, accounting for potential lensing effects that could magnify brightness. They are running new simulations with updated physics. The model is not dead. It is under interrogation. And this is the moment science lives for. Not when everything fits, but when something resists. Because resistance reveals structure. Webb has not shattered cosmology into pieces. It has pressed its face against the glass and revealed a universe that may be more aggressive, more efficient, more precocious than we dared assume. And as we absorb that, something shifts inside us. The cosmos becomes less like a slow-growing tree and more like a flash of wildfire that established forests almost immediately. We are not watching the first sparks. We are seeing embers from an inferno that raged when time itself was young. And that realization doesn't diminish us. It situates us. We are latecomers in a universe that may have been thriving far earlier than we imagined. Not fragile, not hesitant, but bold from the beginning. And we are only just beginning to understand how bold. Now imagine standing on a shoreline 13.4 billion years ago. There are no oceans yet, no Earth, no Sun, no Milky Way as we know it. Only expanding space, hydrogen and helium flowing through invisible rivers of dark matter. The universe is still less than 3% of its current age. And already, according to Webb, vast stellar furnaces are burning. We used to think of the first billion years as a prologue. It may have been Act 1. To feel how radical that is, we need to revisit what early actually means in cosmology. The Big Bang was not an explosion into space. It was the expansion of space itself. Every region stretched away from every other region. In the first fractions of a second, inflation may have blown quantum fluctuations to cosmic size. Then came a hot plasma era, nucleosynthesis forging the first light elements, recombination freeing photons, the long dark ages before the first stars. That sequence is still intact. Webb is not erasing the Big Bang. It is challenging the pacing. Because after recombination, gravity had to amplify those tiny fluctuations in density, 1 part in 100,000, into galaxies containing billions of stars. That amplification depends on how quickly matter can collapse and cool. If early galaxies are heavier than predicted, then amplification happened faster. That suggests one of 3 things. Either the initial fluctuations were slightly different than we think, unlikely given how precisely the microwave background maps them, or baryonic physics, the behaviour of normal matter, operates more efficiently under early conditions, or our understanding of dark matter and expansion history needs refinement. Each path leads somewhere profound. Let's follow the second one first, baryonic physics. Gas cools by radiating energy. In the early universe, pristine gas consisted almost entirely of hydrogen and helium. Without heavy elements, cooling channels are limited. That should slow star formation. But molecular hydrogen can form in small amounts, enabling gas clouds to shed heat and collapse. If the first stars were extremely massive, hundreds of solar masses, they would live fast and die in violent supernovae within a few million years. Those explosions would inject heavy elements into surrounding gas, dramatically increasing cooling efficiency for subsequent generations. Star formation begets enrichment. Enrichment begets more efficient star formation. Galaxies could bulk up quickly. Simulations are now exploring this possibility in detail. Adjust feedback prescriptions. Allow gas inflows to be smoother. Reduce the disruptive impact of supernova winds in dense early halos. Some models can indeed produce more massive early galaxies, though often at the edge of parameter space, which is science's way of saying possible but tense. Now follow the third path, dark matter and expansion. Dark matter makes up about 85% of the universe's matter content. It does not emit light. It interacts primarily through gravity. Its nature remains unknown. In the standard picture, dark matter is cold, moving slowly compared to the speed of light in the early universe. That allows small structures to form early. But what if dark matter had subtle interactions? self-scattering, decay, coupling to radiation that altered early collapse rates? What if dark matter clumped slightly more efficiently at small scales? Or what if, during the first few 100 million years, there was a brief episode where expansion slowed relative to expectations, giving gravity more time to work? Even a small deviation in the expansion rate could significantly impact structure growth. This is where the Hubble tension re-enters the story. Local measurements suggest the universe is expanding faster today than predicted from early universe parameters. One proposed solution is early dark energy, a temporary energy component present before recombination that subtly altered expansion and then faded away. If such a component existed, it would modify how density fluctuations grew. Perhaps Webb is glimpsing consequences of physics we are only beginning to parameterize. And then there is the most dramatic possibility, one that researchers discuss carefully but cannot ignore. What if some of these early galaxies are not just massive, but contain black holes that form through pathways we have never directly observed? Supermassive black holes at redshifts above 7 already challenge growth timescales. To reach 1 billion solar masses in under 1 billion years, accretion must be relentless, or seeds must be huge. If the first black holes formed via direct collapse of massive gas clouds, skipping the normal stellar phase, they could begin life at 10,000 to 100,000 solar masses. From there, rapid accretion could produce quasars astonishingly early. And black holes are not passive. As they feed, they release enormous energy: jets, radiation, winds. That energy can compress surrounding gas, potentially triggering further star formation under certain conditions. In this view, early black holes are not obstacles to galaxy growth. They are catalysts. If that mechanism operated efficiently, the early universe could have undergone bursts of synchronized star formation anchored by rapidly growing black holes. This paints a different portrait of cosmic dawn, not isolated sparks, but clustered ignition points. Now pull back. When we say shattered cosmology, what we really mean is that a model comfortable in its success has encountered data that force humility. The standard cosmological model has survived decades of scrutiny. It explains the large-scale structure of the universe, the abundance of light elements, the microwave background, gravitational lensing, baryon acoustic oscillations. It is one of the most successful scientific frameworks ever built. Webb is not demolishing it. It is probing its edges. And edges are where revolutions begin. Think of past moments like this. When Edwin Hubble discovered that distant nebulae were actually galaxies beyond the Milky Way, the universe expanded overnight. When cosmic acceleration was discovered in 1998, dark energy entered the lexicon and rewrote our fate. Each time, the data did not politely confirm expectations. They forced expansion of thought. Webb feels like that kind of instrument. It is not just collecting images, it is interrogating origins. And the interrogation is far from complete. Some early galaxy candidates have already been revised downward in mass after more precise measurements. Others remain astonishing. Future observations with gravitational lensing, using galaxy clusters as natural magnifying glasses, will reveal even fainter populations. We may discover that early giants are rare outliers, or we may confirm that they are common. That difference matters, because rarity can be accommodated. Abundance demands revision, and here is the human heartbeat inside all of this. We are watching the universe rewrite its childhood in real time. For generations, we taught that complexity required billions of years of gradual accumulation, that galaxies like ours were late achievements of cosmic patience. Now we are entertaining the possibility that the universe was capable of building grand structures almost immediately. That does not diminish the grandeur of the present. It deepens it. Because if complexity emerged quickly, then the cosmos is not hesitant. It is generative. It does not inch towards structure. It lunges. And we, beings of carbon and thought, are products of that lunge. There is something profoundly grounding about that. We are not anomalies perched on the far edge of improbability. We may be expressions of a universe that tends towards structure wherever gravity, time, and matter are allowed to interact. But humility remains essential. The data are young. Webb has been operational for only a short time, relative to the decades over which our cosmological framework matured. The interpretation of faint infrared light at extreme redshift is complex. Stellar population models are being recalibrated. Dust properties at early epochs are not fully constrained. The universe may yet settle into consistency with the standard model, or it may reveal subtle deviations that cascade into new physics. Either way, we are witnessing the sharpening of understanding, and that is its own kind of awe, because somewhere 13.4 billion years ago, light left a galaxy that should not have existed. It travelled across expanding space. It thinned, it reddened, it stretched. And tonight, in a control room on Earth, that ancient light lands on detectors cooled near absolute zero. We translate it into numbers, into spectra, into images. And we realise that the universe's first chapters were not quiet rehearsals. They were declarations, and we are only just learning how to read them. There is a moment when you stare at one of Webb's deep field images where your brain quietly gives up. At first, it looks like noise, scattered points of red and gold, smudges, arcs. Then you realise almost every dot is a galaxy. Not a star, a galaxy. Hundreds, thousands, each containing billions of stars. And hidden among them are the oldest structures ever seen. Light that left when the universe was so young it had barely learned its own laws. We are not just observing distance. We are observing origin pressure. Because the early universe was dense, mean matter density scales with the cube of the scale factor. Go back to when the universe was 1/10 its current size, and density increases by a factor of 1,000. 1,000 times more matter packed into each volume. Gravity thrives in density. So perhaps we underestimated just how aggressive collapse could be under those conditions. Perhaps early halos were not timid seedbeds, but violent wells, pulling in gas in torrents. Picture waterfalls of hydrogen plunging into dark matter basins. Shock fronts igniting starbursts. Radiation blasting outward, carving ionized bubbles through intergalactic space. Reionization, the era when ultraviolet light from early stars stripped electrons from hydrogen across the cosmos, may not have been a slow sunrise. It may have been a rapid blaze. Measurements of the microwave background suggest reionization occurred around 500 to 700 million years after the Big Bang. Webb is now revealing candidate galaxies capable of producing enormous quantities of ionizing photons even earlier, which raises the possibility that reionization began sooner than we thought. The universe may have cleared its fog faster, and that has implications for how transparent space became, how radiation travelled, how structure interacted. But beneath all of this technical recalibration is a deeper shift. For decades, cosmology felt settled, not finished, but stable. Parameters measured to percent precision, simulations matching surveys, a standard model with only a few unknown ingredients: dark matter, dark energy, inflation. We knew we were missing pieces, but we felt confident in the scaffolding. Webb did something dangerous to confidence. It made the early universe look ambitious, and ambition invites revision. There is a psychological dimension here. Humans like gradualism. It mirrors our own development, childhood, adolescence, adulthood. We assume the cosmos matured similarly, but the universe may not mirror us. It may erupt, and then refine. Consider how quickly structure forms in other extreme systems. In a collapsing molecular cloud within our galaxy, stars can form in a few million years. In galaxy collisions, tidal forces can ignite starbursts almost instantly on cosmic timescales. The universe, when conditions are right, does not hesitate. So perhaps the real surprise is not that early galaxies are massive. Perhaps the surprise is that we underestimated gravity's impatience. Yet even if baryonic physics explains part of this story, the tension with predicted halo mass functions remains. The abundance of massive dark matter halos at very high redshift should drop steeply. Seeing several luminous candidates suggests either observational bias or new insight into how luminous galaxies trace underlying halos. Gravitational lensing complicates the picture. Some early galaxies may appear brighter because intervening mass magnifies them. Webb teams account for this, but subtle lensing effects can skew interpretations. Stellar population modelling is another frontier. At extreme redshift, we rely on spectral energy distributions, colours across infrared bands, to infer age, metallicity, and mass. If early stellar populations behave differently, if, for example, they contain a higher fraction of very massive stars, the light-to-mass ratio shifts. A galaxy could appear more massive than it truly is. But even after corrections, some objects remain remarkably substantial. And this is where the phrase different universe begins to feel less hyperbolic. Not because the laws of physics are overturned, but because our mental portrait of the first billion years is transforming. We once imagined a sparse cosmos slowly knitting itself together. Now we are contemplating a universe that reached structural maturity with startling speed. And that reframes our cosmic identity. We often say we live in a middle-aged universe. Stars are still forming, but at a lower rate than in the past. The cosmic star formation rate peaked around 10 billion years ago and has declined since. If early galaxies were already highly active, then the rise toward that peak may have been steeper than expected. The universe's adolescence may have been intense, violent, productive, which means the cosmic environment that eventually gave birth to the Milky Way was shaped by early generations of galaxies far more dynamic than we assume. Our galaxy is not an isolated achievement. It is a descendant of ancient brilliance. And then there is the philosophical undercurrent. If cosmology adjusts, if expansion history tweaks, if dark matter properties refine, if early star formation proves hyper-efficient, it will not diminish science. It will demonstrate its strength. Because the model changes when reality insists. That is not fragility. That is resilience. Still, we must resist the temptation to declare revolution prematurely. History reminds us that first impressions of extreme observations often soften with time. Calibration improves, biases reveal themselves. Extraordinary outliers become rare exceptions rather than rule breakers. But sometimes, data do signal a deeper shift. We do not yet know which path Webb's discoveries will ultimately take. What we do know is this: the early universe was not featureless. It was fertile. And fertility changes everything. Because fertility implies potential. Potential for stars, for planets, for chemistry, for complexity. Stand in the present and look backward across 13.8 billion years. You are not gazing into a void. You are gazing into an origin that may have been far more productive, far more structured, far more daring than we allowed ourselves to imagine. It compresses cosmic loneliness. If galaxies assembled quickly, if heavy elements circulated early, if planetary systems could form sooner, then the timeline for habitable environments widens. The universe had time, perhaps more time than we thought. Not necessarily for intelligence, not necessarily for life, but for possibility. And possibility is enough to change how we feel beneath the stars. Because the night sky is no longer a quiet museum of distant relics, it is a record of a universe that began building almost immediately. A universe that did not wait. A universe that may have been different in its youth, not in law, but in tempo. Faster, brighter, bolder. And we are only at the beginning of understanding how bold it truly was. There is one more layer beneath all of this, and it is the one that makes cosmologists lean back in their chairs and go quiet. It is not just that galaxies appear earlier, it is how confidently we thought we knew they wouldn't. Before Webb launched, researchers ran simulations of the early universe using the best available data, Planck measurements of the cosmic microwave background, constraints on matter density, dark energy fraction, baryon content. These simulations produce statistical predictions, how many galaxies of a given mass should exist at a given redshift. The numbers were not guesses. They were extrapolations from a framework that had survived every major test for decades. So when Webb began returning images suggesting an unexpectedly high number of bright, massive candidates at redshifts above 10, the tension wasn't casual. It was structural. Imagine predicting how many skyscrapers should exist in a city based on population growth, economic output, material availability, and then discovering entire districts you didn't budget for. Either your census is wrong, or your growth model is incomplete. The early Webb results hinted at more bright galaxies than predicted. Some analyses suggested an order of magnitude difference at certain mass ranges. An order of magnitude. In cosmology, that is not rounding error. Now the community moved quickly. Revised photometric techniques, improved spectral confirmation, refined stellar population assumptions. Some early candidates were downgraded, some disappeared, but not all. And that persistence is what keeps the conversation alive. Because cosmology is constrained not just by galaxy counts, but by the smoothness of the microwave background and the distribution of large-scale structure billions of years later, any change to early structure formation must propagate consistently forward in time. You cannot simply insert more early galaxies without consequences. They would leave gravitational fingerprint. They would alter reionization history. They would shift clustering statistics. Which means if Webb's early giants are real and common, then the adjustment must be subtle but global. This is where early dark energy models gain emotional gravity. The idea is elegant. Introduce a small, temporary component of energy density in the early universe that changes expansion dynamics just enough to resolve the Hubble tension and potentially influence structure growth. This component fades away before dominating later epochs. It's a whisper in the equations, but whispers at the beginning echo across billions of years. Alternatively, perhaps star formation efficiency at high redshift is simply far more extreme than our lower redshift intuition prepared us for. Maybe early gas accretion rates were relentless, fueled by dense cosmic filaments feeding galaxies continuously. Cold streams of gas plunging directly into halos without shock heating, delivering material faster than feedback could expel it. If so, then the early universe was not just dense. A web of supply lines feeding rapid construction. And that idea has beauty. Because the large-scale structure of the universe, the cosmic web, is already known to consist of filaments stretching across hundreds of millions of light years. Galaxies form at nodes where filaments intersect. In the early universe, those filaments were narrower, denser, more active. Perhaps we are seeing the natural outcome of that geometry. Rapid enrichment. Rapid illumination. But even as these mechanisms are explored, a deeper philosophical shift is unfolding. For much of modern cosmology, the dominant narrative has been one of simplicity at the beginning. A nearly uniform universe, tiny fluctuations, slow amplification. Now, the beginning is beginning to look crowded. Not chaotic, but busy. And busyness changes how we imagine cosmic evolution. Because if the early universe was already teeming with luminous systems, then the path from hydrogen to complexity may be less precarious than we thought. The barrier between simplicity and structure may be lower, and that has consequences for how we think about emergence. Consider this. Complexity in physics often arises spontaneously when conditions cross thresholds. Snowflakes form intricate patterns when water vapor cools below a critical temperature. Turbulence erupts when flow exceeds a certain velocity. Life on Earth emerged relatively quickly once the planet stabilized. Maybe galaxies are similar. Maybe once density and cooling conditions cross a threshold, structure cascades rapidly. Maybe the early universe crossed that threshold sooner than expected. And here is the quiet revelation inside all of this. Even if the standard model survives intact, even if revised stellar models and refined mass estimates ultimately reconcile Webb's findings without invoking new physics, the emotional universe has already changed. We have seen farther back than ever before. We have seen that the first few 100 million years were not blank. They were creative. And that realization alters how we feel about cosmic time. 13.8 billion years no longer feels like an unimaginably long prelude before anything interesting happened. It feels like a continuous story of rapid beginnings and sustained evolution. We often imagine ourselves as living near the climax of a long narrative, but perhaps the universe peaked in activity early, in star formation intensity, in structural growth rate. Perhaps we are living in a quieter chapter, a reflective one. The fireworks happen near the start, and their echoes still shape us. There is humility in that thought, because every atom in your body passed through multiple generations of stars. Some of those ancestral stars may have formed far earlier than we once believed possible. The carbon in your cells may trace lineage back to galaxies born in that first cosmic surge. You are not just a product of deep time. You are a descendant of early ambition, and that reframes our place in the cosmos. We are not perched at the fragile edge of improbability in a reluctant universe. We are participants in a cosmos that may have always leaned toward structure, leaned toward light. Yet the mystery remains alive. Upcoming surveys with Webb will push to even higher redshifts. Spectroscopic campaigns will refine metallicity measurements. The Nancy Grace Roman Space Telescope will map wide areas, testing whether early massive galaxies are rare outliers or common features. Ground-based telescopes with 30-meter mirrors will probe dynamics in unprecedented detail. And theoretical physicists will continue adjusting equations, exploring parameter spaces, testing alternatives. This is not the end of cosmology. It is the beginning of a sharper era. Because when observation and expectation collide, understanding accelerates. And we are living inside that acceleration. The universe has not become stranger. It has become more vivid, more immediate, more alive in its youth. The first light was not a timid flicker. It may have been a blaze. And somewhere, across billions of light years, ancient photons are still arriving, carrying stories from a time when everything was new and already astonishing. We catch them. We decode them. And slowly, carefully, we let the universe tell us who it has always been. Not simple, not hesitant, but bold from the very beginning. And as the data accumulate, as models adjust, as debates sharpen, one truth remains steady. We are small. We are late. But we are inside a universe that built grandeur almost as soon as it could. And we are finally capable of seeing it. And here is the quiet pivot, the one that turns this from an astronomical update into something almost existential. If the early universe built massive galaxies faster than expected, then time itself feels different. For decades, cosmic time felt spacious. There was room for gradualism, room for mistakes, room for improbability to compound slowly into complexity. Now imagine a universe where, within a few 100 million years, barely a cosmic blink, gravity had already assembled billion star systems. That compresses the drama. It suggests the cosmos does not require leisurely pacing to achieve magnificence. It suggests magnificence may be its default response. Think about the energy involved. A galaxy forming stars at 100 solar masses per year converts enormous quantities of gas into fusion engines. Each massive star burns hotter and shorter than our Sun, forging heavy elements in its core before exploding. A single supernova releases more energy in seconds than our Sun will emit in its entire 10 billion year lifetime. Now multiply that by millions. That was happening when the universe was still in its infancy. The early cosmos was not dim. It was detonating with creation. And that reframes the phrase cosmic dawn. Dawn implies softness, a slow rise of light over darkness. Webb is hinting at something closer to ignition, an ignition that may have reshaped intergalactic space rapidly, heating it, ionizing it, structuring it. And once you accept ignition, another realization follows. If galaxies were assembling and enriching themselves early, then the conditions necessary for planets, rocky, metal-rich worlds, could have emerged earlier too. Planet formation requires heavy elements, iron for cores, silicon for crusts, oxygen, carbon, nitrogen for chemistry. These elements are the ash of dead stars. If those stars lived and died quickly, then planetary ingredients circulated quickly. It does not mean life arose early, but it means the stage could have been set. And that extends the timeline of cosmic habitability dramatically. We used to imagine Earth forming roughly 9 billion years after the Big Bang, as comfortably late, but not extraordinary. Now consider the possibility that other worlds, metal-rich, potentially Earth-like, could have formed billions of years before ours. The universe may have had a head start. But it shifts the emotional scale, because it means the cosmos may have been chemically ready for complexity far earlier than our intuition allowed. And that realization makes our existence feel less like a singular miracle and more like a late chapter in a very long, very active story. But before we let imagination run too far, we return to discipline. Webb's discoveries are data points, not declarations of a new physics textbook. The standard cosmological model remains astonishingly robust. Its predictions match observations across scales spanning billions of light years and billions of years. What Webb has done is expose stress points. And stress points are precious, because they show us where to look harder. Already, teams are refining stellar population synthesis models specifically for extremely low metallicity environments. They are incorporating binary star evolution, which can significantly alter luminosity and lifetimes. They are improving dust modeling in primordial galaxies. They are re-examining assumptions about initial mass functions, how many massive stars form relative to smaller ones. Each refinement tightens the comparison between theory and observation. And this is how science evolves. Not through collapse, through correction. But step back from equations for a moment. Feel the scale. The light Webb captures left its source before Earth existed, before the Sun formed, before the Milky Way acquired its current spiral arms. It travelled for more than 13 billion years through expanding space, stretched from ultraviolet into infrared, diluted across cosmic distances. It survived everything, and now it lands on detectors chilled to near absolute zero in a spacecraft orbiting far beyond the Moon. That is not just engineering. That is continuity across time. We are intercepting messages from the universe's childhood. And those messages are more dynamic than expected, more structured, more luminous. There is something profoundly stabilizing about that. Because while models adjust and debates unfold, one truth deepens. The universe is capable of extraordinary organization under extreme conditions. It did not wait for billions of years to discover how to build. It began almost immediately. And that realization softens the shock. Instead of cosmology shattered, what we may actually be witnessing is cosmology maturing, moving from broad strokes to finer resolution, from smooth curves to textured detail. The early universe was never simple. It was only distant. Now it is visible. And visibility changes perception. The phrase different universe lingers, not because the laws are overturned, but because our mental image of the first billion years is transforming. We are replacing emptiness with activity, replacing sparsity with density, replacing gradualism with urgency. And in doing so, we are forced to update our own narrative instinct. Because if the universe built grandeur quickly, then complexity is not a rare accident that required endless patience. It is something that emerges naturally when gravity and matter are given space and time, even short spans of it. That does not diminish the improbability of life. It does not guarantee companionship in the cosmos, but it reframes the backdrop. We live in a universe that leaned towards structure from the start. That is the quiet revolution Webb has begun. Not a destruction of cosmology, a reanimation of it. The early universe is no longer a blank prologue. It is a dramatic opening act, and we are only now hearing the first lines clearly. The rest of the script is still unfolding, photon by photon, spectrum by spectrum, simulation by simulation. But already, something has settled inside us. We are small. We arrived late, but we belong to a cosmos that was bold almost immediately, a cosmos that built galaxies when it was barely awake, a cosmos that forged the atoms of our bodies in systems that may have existed far earlier than we ever imagined. And as we continue to look deeper, farther back, closer to the beginning, we may find that the universe was never quiet. It was always becoming, always assembling, always daring to be more complex than expected. And the most astonishing part is this. We are here, at the far edge of that unfolding, conscious enough to notice that the beginning may have been even more magnificent than we dared to believe. Now let's slow down, because when we say, this discovery shattered cosmology, what we are really describing is a collision between expectation and reality. And collisions are clarifying. For nearly half a century, the standard model of cosmology, lambda, cold, dark matter, has been the reigning architecture. It says the universe is composed of about 5% normal matter, 27% dark matter, and 68% dark energy. It says structure grows hierarchically. Small objects form first, then merge into larger ones. It says the early universe was simple, nearly uniform, with tiny density fluctuations that gravity slowly amplified. It has been spectacularly successful. It predicted the acoustic peaks in the cosmic microwave background. It predicted the large-scale distribution of galaxies. It predicted the abundance of light elements. So when Webb began hinting that fully developed massive galaxies may have existed only 300 to 400 million years after the Big Bang, the tension wasn't about one dataset. It was about the coherence of an entire framework. If those galaxies are truly as massive and as common as early results suggested, then either we underestimated how fast baryonic matter can convert into stars, we misjudged how dark matter halos assemble at extreme redshift, or the expansion history of the universe includes subtleties we have not fully accounted for. Each option is profound. But notice something important. None of them require abandoning the Big Bang. None of them require discarding relativity. None of them demand that physics breaks. They require refinement. And refinement is not weakness. It is evolution. When Hubble discovered the universe was expanding, it doubled the size of reality overnight. When cosmic acceleration was discovered in 1998, we realized the universe is not just expanding, it is accelerating, driven by something we still call dark energy. Each time the universe did not become less comprehensible, it became larger. Webb may be doing the same thing for the first billion years. Instead of a slow, quiet build-up, we are glimpsing intensity. Instead of sparse beginnings, we are seeing density. Instead of fragile early sparks, we are seeing systems that look confident. And that changes the feeling of cosmic time. Imagine compressing the entire history of the universe into a single human lifespan of 80 years. In the old narrative, the first year of life would be quiet, learning to crawl. Only much later would cities rise. In this emerging narrative, by the time the universe is 2 years old, it is already building skyscrapers. That shift matters, because it suggests that structure formation is not delicately balanced at the edge of impossibility. It may be robust, efficient, perhaps even inevitable under the right conditions. And that realization moves us emotionally closer to the universe, not as an anomaly, but as participants in a process that began decisively. The data Webb has been operating for only a short fraction of the time Hubble did. Early interpretations often evolve. Some extreme mass estimates have already been revised downward. Some candidate galaxies turned out to be closer than first thought. Science is self-correcting. But even with revisions, something remains. The early universe is more luminous than expected, and more productive than comfortable. Which means the question shifts from, is cosmology broken, to something far more interesting. How adaptable is our understanding? Because already simulations are incorporating stronger cold gas inflows along filaments. They are experimenting with top-heavy initial mass functions, where massive stars dominate early star formation. They are modelling black hole seeds that form directly from collapsing gas clouds without fragmenting. None of this violates physics. It explores its edges. And at the same time, observational campaigns are testing these models relentlessly. Spectroscopic confirmation of redshifts, stellar population age constraints, metallicity measurements, ionization signatures. The universe is not yielding easily. It is revealing itself layer by layer. And that is what makes this moment powerful. We are watching the boundary of knowledge shift in real time, not because everything was wrong, but because everything was incomplete. There is something almost poetic about that. The early universe was once invisible. Now it is visible. And visibility transforms mythology into measurement. We are no longer guessing what cosmic dawn looked like. We are observing it. And it looks ambitious. Now zoom out. 13.8 billion years. Hundreds of billions of galaxies. Trillions upon trillions of stars. Every atom in your body forged in stellar interiors that may trace lineage back further than we imagined possible. You are not just the product of a long, slow cosmic wait. You may be the descendant of an early surge. And here is the final, stabilizing truth. Even if the standard model bends, even if parameters adjust, even if early dark energy becomes part of the story, the deeper narrative remains intact. The universe began hot, dense, and expanding. Gravity sculpted structure. Stars ignited. Elements formed. Planets emerged. Life arose. Consciousness looked back. Webb has not erased that arc. It has intensified its beginning. The first act of the cosmic story may have been louder, brighter, and more crowded than we thought. And we are only now hearing it clearly. So, no, the universe has not become alien. It has become more alive. Its infancy was not silent. It was radiant. And as more ancient light arrives, stretched, softened, carrying messages across 13 billion years, we will continue refining the portrait. Not to shatter cosmology, but to deepen it. Because the real revelation is not that the universe is different. It is that it was always more extraordinary than our first models could fully contain. We are small. We arrived late. But we are living in a cosmos that built magnificence almost immediately after it could. And we are finally capable of seeing just how quickly the fire began. And now, let's do the one thing we haven't done yet. Let's zoom all the way out. Strip away the telescope. Strip away the equations. Strip away the headlines. What actually happened? A machine we built travelled 1 million miles from Earth. It unfolded a mirror the size of a house. It cooled its instruments to near absolute zero. It opened its eye to wavelengths human beings cannot see. And it looked backward, farther than anything ever built. What it found was not chaos, not emptiness, not fragility. It found structure. Earlier than expected, brighter than predicted, more organised than comfortable. That's the entire shock. Not that physics failed, but that the universe, in its first few 100 million years, appears to have been more capable than we gave it credit for. For decades, cosmology felt like a nearly finished cathedral. The pillars stood firm: Big Bang, inflation, dark matter, dark energy. The stained glass, galaxy surveys, background radiation maps, fit beautifully into place. Webb didn't knock the cathedral down. It shone a flashlight into the oldest stones. And those stones looked denser than we thought. If early galaxies were assembling quickly, then gravity was efficient. If gravity was efficient, then structure formation was not delicate. If structure formation was not delicate, then complexity may not be rare. That doesn't guarantee life elsewhere. It doesn't guarantee civilizations older than ours, but it changes the emotional background radiation of existence. Because for much of the modern era, we quietly assumed that the universe took its time, that it needed billions of years to become interesting. Now we are confronting the possibility that it became interesting almost immediately. 300 million years after the Big Bang. On cosmic scales, that's infancy. That's barely learning to breathe. And already, galaxies may have been blazing with billions of stars. Let that settle. We are not living at the climax of a slow, reluctant story. We are living billions of years after an opening act that may have been explosively productive. The universe did not whisper itself into structure. It may have surged, and that changes how the night sky feels. When you look up, you are not looking at distant, patient objects that took forever to form. You are looking at descendants of an early, furious creativity. Galaxies that may trace their lineage back to systems that matured when the universe was only a few % of its current age. And somewhere in that early blaze, heavy elements formed. Carbon, oxygen, iron. The raw materials of your blood, your bones, your breath. Those elements were forged in stars that may have existed earlier than we ever imagined. Which means your existence is tied not just to deep time, but to rapid beginnings. There is something deeply stabilizing about that, because it suggests the universe is not fragile in its ability to generate structure. It is generative by nature. And here is the quiet resolution. Cosmology is not shattered. It is alive. The standard model may bend at the edges, parameters may shift. Early dark energy may become more than a mathematical possibility. Stellar models may evolve, simulations may become more extreme, but the core story endures. The universe expanded, gravity sculpted, stars ignited. Webb has not broken that arc. It has illuminated its intensity, and that illumination is the real transformation. We are watching the earliest chapters of existence come into focus, not as myth, not as assumption, but as data. And the data say this: the universe was not waiting. It was building. From almost the very beginning. So no, we are not living in a different universe. We are living in a universe that may have been more ambitious in its youth than we ever understood. A universe that did not hesitate to assemble grandeur. A universe that forged the ingredients of life quickly. A universe whose infancy was not quiet darkness, but structured light. And here we are, 13.8 billion years later, standing on a small planet orbiting an ordinary star in a spiral galaxy that itself may be the descendant of ancient systems Webb is only now revealing. We are small. We arrived late, but we are not disconnected from that early blaze. We are its continuation. The photons Webb captures began their journey before Earth existed. They travelled across expanding space for billions of years. They arrive now. We decode them. And in doing so, we realise something profound. The universe did not grow cautious with age. It was bold from the start. And that means the story of existence is not one of slow awakening, but of early brilliance echoing forward through time, until one day, in a corner of a galaxy, the universe became aware enough to look back at its own beginning and discover that it had always been more extraordinary than it imagined. And if we sit with that long enough, something unexpected happens. The shock fades. The panic about cosmology shattered dissolves. What remains is something quieter and far more powerful. Continuity. Because whether the early universe formed galaxies slightly faster or dramatically faster, whether dark matter has subtle new properties or stellar physics needs revision, the deeper truth does not fracture. The universe worked. It worked early. It worked efficiently. It worked without supervision. Gravity pulled. Gas cooled. Stars ignited. Black holes grew. Light flooded the dark. And none of it required us to exist. That is the humbling symmetry of this moment. Webb did not uncover chaos at the beginning. The cosmos did not stumble into structure. It assembled it with startling speed. For years we imagined the early universe as a fragile workshop, delicate fluctuations barely surviving expansion. But the emerging picture feels different. It feels industrial. Filaments channeling matter like supply lines. Dark matter halos acting as gravitational anchors. Star formation erupting in dense clusters. Supernovae detonating, enriching space. Black holes feeding, radiating, influencing their surroundings. An engine already running hot. And if the engine was running hot that early, then what we are living in now is not the universe warming up. It is the cooled aftermath of an early blaze. The peak of cosmic star formation happened billions of years ago. The universe today is quieter, calmer, more spacious. We are living in the long golden hour after the fireworks. And that changes the emotional weight of time. Because instead of imagining ourselves at the crest of cosmic activity, we begin to see ourselves as inheritors, descendants of a universe that surged into structure quickly and then gradually relaxed. That is not a small shift. It reframes everything. It reframes rarity. It reframes habitability. It reframes the sense of isolation we sometimes project onto the cosmos. If the early universe was structurally ambitious, then complexity may not require endless patience. It may require the right conditions, and those conditions may have been common early on. This does not promise neighbours, but it stretches the canvas of possibility. And possibility changes how the night sky feels. Because when you look up now, you are not just seeing distant lights. You are seeing that within a few 100 million years, barely 2% of its current age, it was already generating massive systems, forging elements, reshaping space with radiation. It was already alive with activity. And we are the late echo of that beginning. There is something almost poetic about this symmetry. The earliest galaxies we see are not small and tentative. They are bold. And we, billions of years later, are bold enough to see them. The universe builds. And eventually, it builds observers. Observers who refine its story. Observers who correct their own assumptions. Observers who discover that the beginning was not simpler, only farther away. Cosmology was never broken. It was incomplete. Webb did not shatter it. Webb deepened it. And that is the real transformation. Because every time we push our instruments farther, the universe answers, not with silence, with detail, more structure, more nuance, more reality than our first models contained. And that is the pattern across history. The Milky Way was once the entire universe. Then it became one galaxy among many. The universe was once thought static. Then it was expanding. Then accelerating. Each step did not shrink our place. It expanded it. Now the first billion years are expanding in richness. What was once imagined as dim and sparse now appears vibrant and structured. And we are adjusting. Not collapsing. Adjusting. That is the strength of science. It bends toward truth, even when truth arrives from 13 billion years away. So where does that leave us? Small. Yes. Late. Absolutely. But also connected, because the same physical laws that ignited those early galaxies operate here, in your body, in your brain, in the star that warms this planet. The same gravity, the same fusion, the same cosmic inheritance. We are not outside the story of early brilliance. We are its outcome. The atoms that compose you may have originated in stars born far earlier than we ever imagined possible. You are, quite literally, a late expression of early audacity. And that is not unsettling. It is grounding. Because it means the universe did not slowly stumble toward complexity and accidentally produce consciousness at the edge of improbability. It surged into structure, and given enough time, structure learned to look back. That is the arc. From plasma to galaxies. From galaxies to stars. From stars to elements. From elements to planets. From planets to awareness. And Webb has shown us that the first steps of that arc were faster, brighter, and more assertive than we assume. The universe did not whisper its opening line. It declared it. And now, billions of years later, we are finally hearing the full volume of that declaration. Not a different universe. A deeper one. Not shattered cosmology. A sharpened one. And as more ancient photons arrive, stretched across time, carrying evidence from the earliest epochs, we will continue refining the picture. Because that is what awareness does. It looks, it questions, it corrects, and in doing so, it becomes part of the universe understanding itself. The beginning was not fragile, it was formidable. And we are living proof that its early fire never truly went out. Now let's let the noise fall away completely. No headlines, no algorithms, no dramatic phrasing, just the universe and us. 13.8 billion years ago, everything we know was compressed into a state so hot and dense that atoms could not exist. Space expanded, it cooled, light broke free. Tiny fluctuations, smaller than a fraction of a percent, became the seeds of all structure. For decades, we believed those seeds took their time, that gravity laboured slowly against expansion, that the first galaxies were faint rehearsals. But Webb has shown us something emotionally different. The early universe may not have tiptoed into complexity. He may have accelerated into it. And here is why that matters. Because if structure formation was robust early, then the cosmos is not balanced on a knife's edge of improbability. It is generative. It produces structure when conditions allow. It organises matter when gravity has room to work. It forges complexity when energy flows. That realisation is stabilising in a way few people expected. For much of modern thought, we have wrestled with the idea that we might be an extraordinary accident in an otherwise indifferent, sparsely populated cosmos. But if galaxies assembled rapidly, if heavy elements circulated quickly, if planetary building blocks emerged sooner, not guaranteed, not inevitable, but possible, earlier and perhaps more widely than assumed. And possibility reshapes perspective. Look at the timeline. The Sun formed 4.6 billion years ago. Earth stabilised quickly. Life appeared astonishingly early in our planet's history, perhaps within a few 100 million years after oceans formed. On Earth, once conditions were right, life did not hesitate. It emerged. If the broader universe follows similar thresholds, if complexity ignites when physics allows, then early structure formation expands the window in which such thresholds could have been crossed elsewhere. Again, not proof, but a widening of cosmic time in which chemistry could deepen, planets could cool, atmospheres could form, and perhaps, somewhere, awareness could arise. That is not a small implication. And yet, none of it requires abandoning the foundation of cosmology. The Big Bang remains. Relativity remains. Dark matter remains. Dark energy remains. What changes is tempo. The first billion years may have been more intense than our models first painted. And tempo changes emotion. Imagine two orchestras playing the same symphony. One performs it slowly, gradually swelling. The other begins with a powerful, immediate crescendo. Both reach the same themes, but the experience feels different. Webb is revealing that the cosmic symphony may have opened with a crescendo, and we are hearing it for the first time. Now let's come back to the human scale. Every photon Webb captures travelled for over 13 billion years. It crossed expanding space. It survived the growth of galaxies, the birth and death of stars, the formation of the Milky Way. It survived everything, and it arrived now, at a moment when intelligent beings built a mirror to catch it. That continuity is staggering. The universe began building galaxies almost immediately. Billions of years later, those galaxies built stars. Those stars built elements. Those elements built planets. On one of those planets, chemistry crossed a threshold. Cells formed. Life evolved. Brains emerged. Curiosity ignited. And that curiosity built a telescope capable of seeing back to the beginning. There is no rupture in that chain. There is only unfolding. Webb did not reveal a foreign universe. It revealed our ancestry more vividly. The early blaze that forged the first heavy elements is part of the same story that forged you. If the beginning was brighter than expected, then your existence is tied to a universe that did not delay its creativity. And that changes how smallness feels. Yes, we are small in size. Yes, we are late in time. But we are not disconnected. We are late expressions of early energy. Consciousness is not separate from cosmology. It is one of its outcomes. So when headlines say cosmology shattered, what they are really describing is discomfort. The discomfort of realizing that our mental picture was too quiet. The discomfort of upgrading the beginning from dim to luminous. But upgrade is not destruction. It is refinement. The universe is not breaking its laws. It is revealing their power. Gravity was always strong. Fusion was always efficient. Matter always obeyed the same equations. We simply underestimated how quickly those equations could produce grandeur. And now we know better. Or at least, we are learning. As more data arrive, as spectra sharpen, as simulations evolve, the portrait will become clearer. Maybe the tension will soften. Maybe early galaxies will settle into alignment with revised models. Or maybe a subtle new parameter will enter the equations, an early energy component, a tweak to dark matter behavior, a refinement of star formation physics. Either way, the deeper arc remains intact. The universe began. It structured itself. It enriched itself. It cooled. It continued. And here we are, standing beneath a sky that once looked empty in its youth and now looks full. Not because it changed, but because we finally looked with sharper eyes. The early universe was not fragile. It was formidable. And the discovery of that fact does not diminish us. It situates us. We are the late awareness of an early fire, the echo of a beginning that may have been brighter, faster, and more decisive than we ever imagined. And as we continue to look deeper, closer to the first light, closer to the first structure, we will keep discovering the same thing. The universe was never timid. It was always becoming. And now, at last, we are becoming aware of just how quickly it began. And in the end, what makes this moment unforgettable is not the numbers. It is the reversal. For most of human history, the past felt primitive. Ancient meant simple. Early meant undeveloped. That instinct shaped how we imagined the cosmos too. The early universe must have been crude, sparse, waiting. Webb has quietly inverted that assumption. The first few 100 million years may not have been a rough draft. They may have been a surge, not incomplete, just dense with energy and consequence. And that changes the emotional geometry of time. Because if the universe achieved large-scale structure almost immediately, then the arrow of complexity does not crawl forward. It ignites. It leaps. It cascades. Gravity does not negotiate. When matter can collapse, it collapses. When stars can form, they form. When black holes can grow, they grow. And the early universe had every ingredient packed tightly together. High density, abundant gas, strong gradients. In that environment, hesitation is unlikely. So perhaps the surprise is not that galaxies appeared early. Perhaps the surprise is that we expected them not to. There is a humbling lesson in that. Our intuition evolved on a quiet planet over short timescales. Cosmic processes operate under extremes we rarely experience. Densities thousands of times higher than today. Radiation fields intense. Matter funneling along filaments like rivers of fire. Under those conditions, structure may be not just possible, but rapid. And once we accept that, the shock dissolves into awe. Because the universe did not barely manage to build galaxies. It may have done so with urgency. Which brings us to the final turn. We often think of ourselves as improbably late, consciousness arising in a vast, aging cosmos long after the interesting events occurred. But what if the interesting events began almost immediately? What if the first billion years were the most structurally dynamic chapter of all? Then we are not standing at the fragile tip of a slow crescendo. We are living in the long echo of an explosive opening. The heavy elements in your blood may trace their ancestry back to stars formed when the universe was still a toddler. Your existence is not balanced on a delicate, drawn-out improbability. It is connected to a cosmos that may have been structurally decisive from the beginning. And that is the quiet, emotional resolution. Cosmology is not shattered. It is sharpened. The early universe is not broken. It is more vivid than we imagined. The story did not change its plot. It changed its tempo. And tempo matters, because it tells us something profound about the nature of reality. When conditions allow complexity, the universe does not resist. It proceeds. It organizes. It builds. From quantum fluctuations to galaxy clusters. From hydrogen gas to spiral arms. From supernova ash to living cells. And eventually, to awareness looking back across 13.8 billion years. The James Webb Space Telescope did not reveal a different universe. It revealed that the beginning was not quiet. It was bold. And boldness echoes. It echoes through star formation histories, through chemical enrichment, through planetary formation, through biology, through us. We are not outsiders observing an alien past. We are late participants in an early surge. The photons arriving now left galaxies that should not have existed so soon, according to our first drafts of understanding. But they did exist. They shone. They evolved. They endured. And their light travelled across expanding space to reach a species capable of decoding it. That continuity is the true wonder. The universe did not merely expand. It elaborated. It did not merely cool. It structured. It did not merely survive. It flourished. Earlier than we expected. Faster than we assumed. And that realization leaves us with something deeper than shock. It leaves us with alignment. A cosmos that did not hesitate to ignite. A cosmos that forged complexity almost as soon as it could. And now, billions of years later, in a quiet corner of a spiral galaxy, that same cosmos is awake enough to recognize that its beginning was more magnificent than it ever imagined. So let's leave it here. Not with panic, not with collapse, not with shattered equations scattered across the floor, but with clarity. The James Webb Space Telescope looked back to within a few 100 million years of the Big Bang and found galaxies that appear larger, brighter, and more structured than expected. That is the fact. From that fact, tension emerged. From tension, refinement began. And from refinement, something extraordinary surfaced. The early universe may have been more efficient at building structure than our first models assumed. Not lawless. Not chaotic. Efficient. That word changes everything. Efficiency means gravity did not struggle. It means gas did not hesitate. It means stars ignited rapidly under dense conditions. It means black holes may have formed and grown with startling speed. It means heavy elements, the raw materials of planets and life, may have circulated earlier than we believed. And if that is true, then the first act of the cosmic story was not a quiet prelude. It was a declaration. A universe barely 2 to 3% of its current age, already assembling systems of staggering scale, already shaping the architecture that would ripple forward for billions of years, already setting the stage for everything that followed. There is no destruction in that revelation. There is expansion. Our mental picture expands. Our timeline deepens. Our assumptions sharpen. Because the standard cosmological model remains intact in its core structure, the Big Bang, inflation, dark matter, dark energy, expansion, structure growth. But Webb has forced us to confront the possibility that the earliest chapter was more intense than we rehearsed, more luminous, more crowded, more productive. And that matters emotionally, because it suggests the universe did not take eons to discover how to build. It knew how to build almost immediately. Gravity did not need practice. Fusion did not need rehearsal. Complexity did not need coaxing. Under the right conditions, it surged. And that surge is not separate from us. The oxygen in your lungs, the iron in your blood, the carbon in your cells, all of it forged in stars that descend from that early structural explosion. You are not standing outside the universe looking at an ancient anomaly. You are a late expression of early confidence, a product of a cosmos that began organizing itself with startling ambition. So no, we are not living in a different universe. We are living in a universe whose infancy was more magnificent than we assumed. A universe that did not whisper its beginning. It ignited it. And now, billions of years later, we are here, small, late, finite, but conscious enough to recognize that ignition. The photons Webb captures are not just data, they are continuity. They left their galaxies when the universe was young and racing. They crossed expanding space for over 13 billion years. They arrive now. We measure them. We revise our models. We refine our story. And in doing so, the universe becomes clearer. Not simpler. Clearer. It is not fragile. It is formidable. It did not crawl toward complexity. It lunged. And eventually, in one unremarkable spiral galaxy, that lunging universe produced minds capable of asking how quickly it began. That is the real resolution. The cosmos was bold from the start, and we are its awareness, arriving late but not disconnected. We are the echo of an early blaze, the continuation of an initial surge, the quiet consciousness of a universe that built magnificence almost as soon as it could. And the more deeply we look, the more we realize the beginning was never empty. It was already extraordinary. And we are still living inside the momentum of that first brilliant act. And if we let the story come to rest, not with shock, not with headlines, but with perspective, something even larger comes into focus. The James Webb Space Telescope did not uncover chaos at the edge of time. It uncovered capacity. The capacity of gravity to organize matter quickly. The capacity of gas to cool and collapse under extreme density. The capacity of the universe to generate light almost immediately after darkness lifted. For decades, we imagined the first billion years as a slow climb out of simplicity. Now we are confronting the possibility that it was a rapid ascent into structure. That shift does not dismantle cosmology. It enriches it. Because cosmology was never meant to be static. It is a living framework, refined whenever new light arrives. And Webb has delivered older light than any instrument before it. Light from galaxies that may have existed when the universe was only 300 million years old. Light from systems that appear far more mature than anticipated. And here is the deeper emotional truth behind all the modelling, all the debates, all the recalibrations. The universe was not waiting to become magnificent. It was magnificent almost immediately. That does not mean every galaxy was massive. It does not mean every region was crowded. But it means the processes that lead to grandeur were already active, already efficient, already unstoppable, which changes how we understand our own emergence. Because if complexity arises readily when the conditions allow, then consciousness is not an isolated miracle balanced on cosmic hesitation. It is an outcome of sustained structure. The early universe built stars. Stars built elements. Elements built chemistry. Chemistry built biology. Biology built awareness. And awareness built a telescope capable of seeing back to the beginning. There is no rupture in that chain, only continuation. Webb's discovery feels dramatic because it compresses our mental timeline. It forces us to imagine a universe that did not slowly practice creation. It practiced it instantly. And that realization leaves us with something steadier than shock. We are not late intruders in a tired cosmos. We are participants in a universe that has been structurally ambitious from the start. The early galaxies Webb sees are not alien anomalies. They are ancestral expressions. They are part of the same cosmic arc that produced the Milky Way, part of the same arc that produced Earth, part of the same arc that produced us. And that arc remains intact. The Big Bang still anchors it. Relativity still governs it. Dark matter still sculpts it. Dark energy still stretches it. What has changed is our appreciation for how quickly it all began. The first act was not dim, it was decisive. The first chapter was not blank, it was active. The first structures were not tentative, they were bold. And now, standing here in the long afterglow of that beginning, we are finally able to see it. Not through myth, not through assumption, but through light that has travelled for over 13 billion years to reach us. And that light carries a message more powerful than any headline. The universe did not hesitate to build. It did not require endless patience to generate complexity. It moved. It organised. It ignited. And we are living inside the momentum of that ignition. So the story does not end with cosmology shattered. It ends with cosmology awakened, sharpened, deepened. The universe remains vast. We remain small. Time remains immense. But the beginning is no longer quiet in our imagination. It is vivid. And in that vividness, something settles. We are not isolated accidents perched on the edge of improbability. We are late expressions of an early blaze. The cosmos was bold from the start. And now, finally, we can see just how bold it was. And now, let the scale finish its work. 13.8 billion years. That number used to feel like distance. Now it feels like momentum. Because what Webb has shown us is not simply that galaxies existed early. It has shown us that the universe did not waste time. Within a few 100 million years, barely 2% of its current age, gravity had already assembled massive systems. Stars were already forging heavy elements. Black holes were already anchoring luminous cores. That is not fragility. That is velocity. And velocity changes how the whole arc feels. We once imagined the early universe as a long, dim corridor leading slowly toward complexity. Now it looks more like a launch, a rapid ignition, a burst of structure that set the tone for everything that followed. The implications ripple outward. If early galaxies were common and bright, reionization may have been swift. If star formation was extreme, heavy elements circulated quickly. If black holes formed early, galaxy evolution began with intensity. And if all of that is true, then the universe did not tiptoe into the conditions necessary for planets. It accelerated toward them. Not deliberately, not consciously, but inevitably under its own laws. That is the quiet magnificence of it. No guiding hand, no adjustment. Just gravity, matter, energy, obeying equations and producing grandeur almost immediately. And somewhere in that early blaze, the chain began that would eventually lead here. The oxygen you breathe may trace its lineage to stars born in galaxies that formed when the universe was barely awake. The iron in your blood may have been forged in systems Webb is only now resolving. You are not separate from that era. You are its continuation. And that is where the emotional resolution settles. Because different universe suggests alienation. But what Webb has actually revealed is connection. The early cosmos was not alien. It was active. It was fertile. It was structurally confident. And the fact that we underestimated that confidence says more about our imagination than about the universe. We tend to project hesitation onto the past. The universe does not hesitate. When density is high, gravity collapses. When collapse occurs, stars ignite. When stars ignite, complexity begins. It is not fragile. It is procedural. And now, with instruments capable of seeing the first few 100 million years directly, we are confronting that procedural boldness in real time. Cosmology is not collapsing under this pressure. It is adapting. Parameters will tighten. Models will evolve. Simulations will grow more extreme. Perhaps a subtle new ingredient will enter the equations, a brief early energy component, a refinement of dark matter behavior, a sharper understanding of stellar physics. But the arc holds. The universe expanded. It structured itself rapidly. It enriched itself early. It cooled gradually. It continued. And eventually, in a quiet spiral galaxy, awareness emerged. That awareness built a mirror. That mirror caught ancient light. And that light revealed that the beginning was more magnificent than we imagined. Small. Late. But not insignificant, because we are not observers outside the cosmic story. We are part of its trajectory. We are what happens when early structure persists long enough to reflect on itself. The universe did not whisper its first chapter. It declared it. Webb has simply allowed us to hear the volume for the first time. And as we listen, photon by photon, spectrum by spectrum, the picture will sharpen further. Not into chaos, into clarity. The early universe was not empty. It was alive with formation. Not hesitant, not tentative, but bold. And that boldness echoes through every star, every galaxy, every atom, every breath. We are not living in a broken cosmology. We are living in a universe that began building almost immediately, a universe that did not wait to become extraordinary. And now, at the far edge of that unfolding, it has become conscious enough to realize that its beginning was brilliant from the start.